Hello, everyone. My name is Alan. I'm a fourth-year PhD student at Texas A&M University. This talk is on our recent work, a mixed integer conic program for the moving target traveling salesman problem based on a graph of convex sets. This work is in collaboration with Professor Siva from Texas A&M University, Professor Ren from Shanghai University, and Professor Howie from Carnegie Mellon University. We consider a motion planning problem where an agent is tasked to intercept a number of moving targets in the most efficient way. This problem has several practical applications. Consider, for example, a robot arm that must pick up moving objects on a conveyor system efficiently. Some other applications include an unmanned aerial vehicle monitoring a number of moving ground vehicles, a UAV defending an area from oncoming hostile rockets or other UAVs, or resupply missions where a resupply ship has to visit patrolling boats. Motivated by practical applications, the moving target traveling salesman problem was introduced in the literature. The moving target traveling salesman problem is a generalization of the traveling salesman problem, or TSP for short. The TSP is a well-studied problem in combinatorial optimization. And the moving target TSP simplifies to TSP when targets are stationary. This makes it NP-hard. And it's generally assumed that the maximum speed of the agent is greater than the speed of any target. The moving target TSP was first introduced in 1998. The authors presented exact and approximation algorithms for very restricted cases. The exact algorithms, for example, required that all targets move on the same line or that all targets move on lines passing through depot. The approximation algorithm assumed that majority of the targets are static. Then in 1999, new approximation algorithms were presented for the very specific case where all targets move in the same direction with the same speed. Recently, in 2022, an exact algorithm, more specifically a mixed integer conic program, was introduced. And this algorithm assumed that each target moves along its own straight line. In fact, this is the case that we are interested in our work. And so we use our work and compare it with this work. We take this work as our baseline. So the problem definition is as follows. We are given a depot and a set of linear target trajectories, and we want to find an agent tour that starts at the depot, visits these moving targets exactly once within their assigned time windows, and then return to the depot. Given a problem instance, we can construct a graph where the nodes represent the target trajectories and the depot, and then add arcs between the nodes. The problem then becomes one of choosing the edges that forms an agent tour, and then finding the times of arrival corresponding to the different nodes. We now look at the baseline mixed integer conic program for the moving target TSP. That we just saw previously. So this formulation is similar to the Miller-Tucker-Zemlin MTZ formulation for the TSP. It relies on big M constraints. The decision variables are as follows. There are the flow variable for arcs. These are binary variables that represent whether an edge is chosen or not. Then there are the cost variables for arcs, which is a non-negative value. And then given any node I, there's a new variable ti, which represents the visiting time for those nodes. Then for any arc E, there are variables lxy and le bar. These are auxiliary variables that are used to define the cost variable for the arc. The formulation is as follows. The objective is to minimize the total path cost. The first few constraints are flow constraint, which ensure that the agent tour starts and ends at the depot and that it visits each node exactly once. The flow conservation constraints ensure that the flow into a target node is equal to the flow out of the target node. Then there are the time feasibility constraints. The time feasibility is a conditional constraint which is satisfied only when an arc is chosen. This constraint says that if an arc E equals to ij is chosen, then the agent should depart from node I at some time ti and reach node j at some time tj, which is greater than or equal to ti, feasibly without violating its maximum speed. If if the arc is not chosen, then no constraints are enforced. To achieve this, big M method is used in this formulation. Similarly, there are other conditional constraints, which is also achieved by big M method. These constraints said that an arc cost is defined by the Euclidean norm if it's chosen, but if it's not chosen, then the arc cost is set to 0. This is a way of switching the arc cost on and off based on whether it is chosen. So our approach is to consider this baseline mixed integer conic program and then formulate this as a non-convex program. We do this by removing the big M method and instead directly using the product of binary and continuous variables. Then we take the non-convex program and further reformulate it as a new mixed integer conic program by convexifying the product of variables. So this is the procedure just for the time feasibility constraint. We look at the big M constraint, and the uppercase T is the big M in this case. So we remove that part of the constraint, and rather we multiply the time variables with the flow variables. Now this has the same meaning, but it is non-convex because of the product of variables. We then convexify this by introducing new variables ZET corresponding to Ti times Ye and ZE prime T corresponding to Tj times Ye. And we ensure that if Ye is 1, then ZET lies within the time window of Ti and ZE prime T lies within the time window for Tj. And when Ye equal to 0, then ZET and ZE prime T goes to 0. And essentially, this whole constraint becomes LE less than or equal to 0. We repeat the same procedure for constraints defining the arc costs. So those are also conditional constraints as we saw before. And one thing to note here is that since the convexification removes variables, the node variables Ti for each node, the continuity of the agent's path needs to be ensured a different way. To do that, we look at the flow conservation constraint and add a time continuity part to it. So this first part ensures that the time at which you visit some node I is equal to the time at which you depart from that node I. So the reformulated mixed integer conic program looks as follows. The objective is unchanged. The flow conservation or the conservation constraints are pretty much the same, but with the added time continuity. And then the time feasibility constraints are convexified as we saw before. And following a similar procedure, we can convexify the arc cost constraint, which says that the cost of an arc is a Euclidean norm if it's chosen and is 0 otherwise. So coming to the numerical experiment, we generated 20 instances randomly for 5, 10, 15, and 20 targets. The first experiment was to vary the time and the duration, and the second experiment was to vary the maximum speed of the agent. The metrics we used were the percentage gap, which shows you the deviation or the gap between the upper bound and lower bound output by a solver. The solver we used was Gurobi. And the other metric was runtime, the average runtime the solver takes to complete the problem. So we compare our mixed integer conic program, MICP GCS, with the baseline, and we saw significant improvement in percentage gap and runtime. So this is the first experiment. our approach is much less affected by increase in time window duration as compared to the baseline. Consider, for example, time window of 50. Here, for 15 targets, our approach converges fully while taking negligible time, while the baseline on average gives a gap even after 1,000 seconds. And even for a time window duration of 75, our approach fully converges for 15 targets in a few minutes as compared to the baseline, which reaches the time limit and still gives a gap of more than 60%. And for 20 targets with 75 time window duration of 75, both approaches reaches the time limit. However, the percentage gap for our approach is less than half of that of the baseline. In experiment 2, we observed that the results appear consistent for different agent speeds. Hence, our approach significantly outperforms the baseline here too, as we saw previously. These are some instances that we use to illustrate. So the left-hand side is our approach and the right is the baseline. We see that our approach gives an optimality gap of 0 in 100 seconds, whereas the baseline reaches 74% gap at the time limit. And this is a 20 target instance. Here too, we have a gap of 30% at time limit as compared to the 80% or more than 80% gap at the time limit for the baseline. We see that the lower bounds are way stronger for our approach as compared to the baseline. So that's the end of the talk, and thank you.